So this is a recent research paper that happened to catch my eye. Rectified HR enabled efficient high resolution image generation via energy rectification. Kind of a long name here. I generally try to stay away from diffusion on my channel for two reasons. Primarily, one, diffusion models tend to be quite large, right? Let's say in the range of 7 billion to 13 billion parameters, which generally speaking doesn't run well on consumer hardware, so it's hard to test out these things. And the secondary reason for me is that to me, the space of diffusion is very well explored from a physics perspective, right? Diffusion as a concept has been around since Sir Isaac Newton. So I don't think, to me, there's going to be a lot of enhancements and like big leaps forward within the diffusion space. That's just my opinion on it. I think that my opinion overall is that like a lot of the gains will be very simple and then just very math oriented gains, right? And there'll be things that like you just would overlook as a general rule. And to me, that's exactly what this rectified HR paper does. And it solves a huge problem that has faced diffusion models for a long time, but the solution ends up being very simplistic, right? And these sets of images, I think, are the best illustration of this concept. And then so if you look at, these are the competing models. So like Demo Fusion, Forescale, HD Diffusion, and Scalecrafter, like these are companies that are big into this niche, right? Where essentially they want to take an image that a model is trained on and then upsize and upscale it via a diffusion process. If you go to like Hugging Face or anywhere else, you'll notice that within a diffusion model, you take your diffusion and it outputs an image, which is generally a very low resolution image. And then you utilize another model that is not a diffusion model to upscale the image from there. And then if you try to do diffusion upscaling itself, the results tend to be poor, as we're looking at with these illustrations here, is what it's showing, right? These examples are showing that when we do diffusion-based upscaling, it runs into issues, and people have been trying to work on this for about 2 years now, and then it's been a bunch of roadblocks. But so this particular research paper, their solution is quite elegant and very simplistic overall, right? They do two things flat out. They do a noise refresh and they do an energy rectification, and then they provide the full math for both of these things. But it's very simplistic in terms of code, right? So here's the code. I wouldn't run this if you have you can't run this if you have the free version of Google Colab, because like again, diffusion models are not small, right? So this is the smallest stability AI. It's Stable Diffusion XL Base 1.0, and then even this wouldn't run within the free version of Google Colab. So you can run this and experiment with it, but it's very straightforward to utilize. So within this, what the model is doing is it's doing two things. It's adding noise, so we have our noise refresh within our steps, and then this rectified HR sampling, which is essentially like so in a lot of my videos, I have made the point that, especially when it comes to diffusion, that diffusion is both a process within thermodynamics as well as fluid dynamics. And then very simplistically within this, what they're doing is, very straightforward, is treating the data more like a fluid in this instance, and the output more as a fluid as opposed to the thermodynamics. Although thermodynamics does come into fluid dynamics, right? And that's what the energy resampling does. But so the noise refresh is very straightforward. Essentially, you take your base image. So in this instance, they have the one of these base images, like this picture of this rocket ship or of the hummingbird, and then so how models work is, if you don't know, like it's the diffusion process, right? So it starts off very blurry and then it denoises the image. And then so let's say halfway through this denoising process, it just adds more noise, Very straightforward, right? It's like, okay, the image is halfway ready, add more Gaussian noise, and then cool. And then that's exactly what happens, right? And then the second equation is like this energy adjustment equation. So when you add this noise, it doesn't necessarily like do anything with regards towards the temperature of the image. So the secondary image says increase the temperature to match the noise, match the increased noise. It's a very simplistic equation. And then by doing that, they upscale images, and the end result is a ability and a model that can upscale images. You can utilize it without retraining the model. So you would just literally run your stable diffusion, like literally just whatever model that you want to run, right? Go to GitHub, pick and I'm picking stable diffusion because it's the most common like open source models. So pick whichever one you want. Whatever model you want, just plug it in here. I would make sure that you're again running to like you're not running on free Google Colab, and then whatever image that you want. Here's your prompt for your image, right? So the default prompt here is a futuristic cityscape with neon lights, and then this is going to upscale your image for you automatically. It's going to be like a high resolution image directly outputted from a diffusion device. So there you go, free of charge. Easy to do this, right? You don't need any sort of app or anything built on top of it. You do need massive amounts of compute, and then that's my drawback when it comes to diffusion overall. So unless you've got like a super powerful computer, this is hard to run. But it's all free. It's all very easy to do, and so here it is overall. Really cool overall improvement. Like congratulations to the authors. It's very like simple and elegant solution, right? Which like I can't frame it enough, and why I make this type of content on this channel, and I dive into these things is for this reason, right? If you understand these things and actually take the time to understand how these things work, it's edge cases and very simplistic, taking a brand new approach and understanding to these things to improve them, right? Like we live in an era of like late stage capitalism where and where the world has been discovered, right? It's like what is that common saying is born too late for like sea exploration and born too early for space exploration, and then so we've lived in a world where like there's not a lot of magic or things to be discovered around these things, right? And then so to me, this is a perfect area of alignment where like that is not true. Where this is a hugely undiscovered area and unexplored area with regards towards physics, mathematics, science overall, and then so computer science, and it all blends together, right? And then so we have an unexplored area that didn't exist before, which to me is overall cool and why I like these things. And so if you like this type of content, please like and subscribe. Thank you very much.